Hi everybody, thank you to be here. Today we welcome Matej. He's working as a postdoctoral student, postdoctoral researcher at Université Catholique de Louvain, and he's going to his work.
Thank you, Louise. Hello everyone. As we said, I'm Matej Mayet from the Institute of Neuroscience at Université Catholique de Louvain. To give a little background on myself, basically. I'm a mechanical engineer, and so I graduated at Sorbonne Université in Paris. And right after graduating, I went to do a PhD at Institut des Systèmes Intelligents et de Robotique, as well as Institut Jean Leron d'Alembert at Sorbonne Université as well, where I studied the interactions with plug string instrument from a perceptual haptic point of view. What I will present here is basically what I have done mainly during my PhD. Yep, that's it. Before going into the details of my work, I think it's important to precise its scope. So my work focuses mainly on studying how touch is solicited while playing the plug string instrument. It is multidisciplinary and addresses topics on both haptics, so the sense of touch, and musical performance. So first of all, one must know that musical performance is an intrinsically multimodal action. Hearing naturally makes sense because musical performance aims at producing a sound that's going to be listened to. Vision plays a crucial role in learning how to play the instrument. It allows the pianist to position his fingers on the keys when learning a new piece. The guitarist to strum a chord on the neck of the guitar, or even to read a sheet. Touch, meanwhile, has a very special place in our relationship with the instrument. Before producing any sound, the musician holds his instrument, he manipulates it, traces its contours, or brushes its surface with his fingertips. When the musician initiates the production of a sound, his fingers rest on the piano keys before pressing them. His lips touch the mouthpiece of the flute before blowing, and the guitar string is deflected before being released by the fingertips. Ultimately, when the musician decides to play the instrument and produce a sound, the body of the instrument vibrates. The same mechanism allowing the instrument to produce a sound transmits a vibratory feedback to the musician through the contact points. And whether the contact with the instrument is localized or more global, whether it is fleeting or sustained, part of the instrument's mechanical energy is transmitted to the musician in this way, and the resulting sensation is an integral part of the musical performance. On another note, the sense of touch is what closes the feedback loop formed by the instrument-musician system, allowing the musician to play in a nuanced and expressive way. And indeed, an interaction with a classical musical instrument is in most cases anything but binary, in the sense that interacting with the instrument in one way or another will not result in the production of the same sound, and that the musician's contribution is not limited to the choice of whether or not to interact with the instrument. The musician is free to add various nuances depending on the sound they are trying to produce or experiment with. And these nuances in sound are reflected in nuances in the strength, acceleration, or position of the musician's movement during playing. To control these nuances as they play, musicians rely at least in part on the haptic feedback provided by the instrument, which allows them to make almost instantaneous adjustments with great precision. And these adjustments are made possible by the exceptional spatial and temporal resolution of the human somatosensory system. So a large body of research aims at recreating the haptic sensations perceived during the play of a classical musical instrument so that it can be simulated through a digital counterpart. And when it comes to simulating phenomena or interactions encountered in our environment, it is first necessary to understand the dynamics specific to the elements implicated in the resulting interaction. In the specific context of haptic interactions with the fingertip, like the pluck of a guitar string, it is crucial to understand what are the forces, displacement, and speeds exerted on the fingertip along the interaction. It allows for the estimation of the nature and amplitude of the haptic cues transmitted, which then guides the choice of an appropriate actuator and the settings required to deliver the corresponding haptic sensation. So here I will take examples a little further away from musical instruments to illustrate my words. Researchers have identified that the perception of roughness comes mainly from the vibrations generated by the unevenness of the surface explored, which then led to the simulation of various textures on flat surfaces using vibrotactile actuators or ultrasonic transducers. Another example, since the human body does not have sensory receptors dedicated to perceiving the moisture of an object or surface, it was necessary to show that the perception of moisture depends largely on the thermal properties of the object or surface with which the skin interacts, and this has led to the creation of devices, still in use today, that simulate surfaces with varying degrees of moisture without using a single drop of liquid. And so one last example I would like to mention on this topic is the simulation of three-dimensional shapes when exploring a flat surface. So about 20 years ago, Delatour and Hayward demonstrated that reproducing the horizontal component of the force exerted on a finger exploring a bump when it is actually exploring a flat surface leads to the sensation of exploring a bump. So this is now a very well-known haptic illusion, and some devices rely on this principle and vary the friction force exerted on the finger by the surface it's exploring in order to generate the sensation of exploring three-dimensional shapes. There is one device in particular that caught my attention, which uses this illusion in an original way. And the study from which the device stems showed that when the skin temperature increases, its viscoelastic properties change, leading in an increase of the real contact area and therefore of the friction force exerted on the fingertip during free exploration. So by placing a heating element under a glass plate, they were able to gradually increase the friction forces when the finger passed over the heating element, creating the sensation of a bump or sticky area at that location, rather than providing thermal feedback. So I had the opportunity to explore this method in greater depth, and as part of an exploratory approach, I sought to estimate the potential of this method to provide adjustable haptic feedback, ideally similar to that felt when running your finger across a moving guitar string. So this preliminary study aimed to observe what types of haptic feedback I was able to generate with this method. And to do this, I set up a parametric study to evaluate the impact of the width of the hearing element, its temperature, and its preheating time on the nature of the perceived haptic stimulus. I therefore designed a device that generated a temperature gradient on the surface of the glass plate using a heating element located just below it. And I analyzed the nature of the haptic feedback perceived during free exploration of the plate by a panel of participants. They had to choose from 4 categories of sensation to describe best what they had felt, whether it was a sticky area, a bump, heat, or an edge. And there was, of course, a neutral category indicating that the participant had felt nothing. The results of this study show that we are indeed able to generate a mechanical stimulus using this method in 80% of the cases, to be precise. But more importantly, this study shows that it is possible to significantly impact the choice of sensation perceived by modulating the heating temperature of the heating element. That said, you can also note that the edge, which among all the available perceptual categories most closely resembles the sensation one might experience when running his finger across a stationary string, remains the least chosen category of all, apart from thermal feedback. And so this particular result led me to think that varying friction through temperature modulation is probably not appropriate for the haptic simulation of plucking a virtual guitar string, and it also highlighted the difficulties inherent in reproducing this interaction. So this led me to pursue a thorough characterization of the plucking interaction, in particular to gain the most comprehensive dynamic and perceptual understanding of it as possible. So a musical instrument string has many variable characteristics. So getting a holistic understanding of such interaction is a long and incremental process. Its length can change, as can its diameter, nominal tension, constituent material, winding, or finish. All these aspects can vary from one instrument to another, but also within the same instrument. These variations in design or implementation influence not only the sound produced by the instrument, but also the visual aspects of the string and potentially the tactile sensation resulting from the interaction. In the specific case of classical guitar playing, the musician has 6 strings at their disposal. In order to enable playing across several octaves, each string has a different nominal tension and diameter from the others. Depending on the musician's subjective preferences or the tone they are seeking to produce, the aspect of the string will also change. Therefore, when the string is plucked and comes into direct contact with the fingertip, depending on the characteristics of the string, the deformations undergone by the fingertip throughout the interaction, and therefore the information transmitted to the sensory receptors innervating the skin, may differ to greater or lesser extent. And so the first part of my work was to provide a perceptual characterization of the plucking interaction. So in order to focus on the perceptual aspects of plucking, I had to establish a list of parameters that are likely to vary between 2 strings on a plucked string instrument. As I said, this list contains a large number of parameters, and part of the preliminary work involved choosing the one with the highest discriminatory potential and therefore the most relevant to study. In the end, I chose to study how our perceived differences between strings differing in their diameter, tension, winding, and the material they are made of. These parameters had to be separated into 2 distinct categories in order to be processed. On the one hand, we have the continuous variables, diameter and tension, and on the other, we have the categorical variables, winding and material. This separation necessarily implied a different approach in the experimental protocol and in the method used to analyze the associated results. I therefore analyzed their perceptual impact through 2 separate studies. For the study of diameter and tension, I sought to estimate the just noticeable differences, which we will refer to as J and D from now on. So I sought to determine the J and D of diameter and tension during plucking. These J and Ds, they allow me to estimate how sensitive the human touch is to these 2 parameters during plucking, or in other words, how perceptually salient these variables are during this interaction. To determine these J and Ds, I built a device that allowed me to present participants with 3 strings in random order, 2 of which were identical and 1 of which was different, either in diameter or tension. During each trial, participants had to blindly pluck the 3 strings in any order and as many times as they wanted during the 20 seconds of exploration time they were given. Once the exploration phase was over, they had to choose the string they perceived as different, which led them to the next trial, a simple 3 AFZ task. Each string was mounted on rails and held at equidistance in a 3-slot resin-made support. An opaque plastic mask was also added between the support holding the strings and the participant in order to eliminate the visual modality, along with noise-canceling headphones for the auditory modality and a damping pedal to limit the transmission of potential vibrotactile signals. Given the continuous nature of the parameters studied, I used the constant stimuli method to estimate the haptic sensitivity of touch to variations in diameter and tension. The reference stimulus for diameter was 0.3 millimeters, to which I compared 5 strings with progressively increasing diameters, and I followed the same process for the tension, but with decreasing values. These diameters and tensions, they were chosen as they were close to those usually found in guitar strings, and the precise values were chosen in order to introduce a certain granularity in the respective differences from the reference string, particularly so that I could estimate our sensitivity to these parameters as accurately as possible. So this graph shows the performance of all participants in the discrimination task. Each black dot represents the average proportion of correct answers from all participants for each diameter difference between the reference string and the comparison string. and each of these small gray dots represent the individual performance of the participants on this task. Since this is a 3AFC, the probability of choosing the different string at random was 33%, so the discrimination threshold was set at 67%. Now, by plotting the psychometric curve adjusted to our point shown here in green, we can estimate the probability that participants will correctly detect this different string for all diameter differences between our extreme values. We can already see that when the diameter difference was small or even non-existent, participants obtain more or less random results around the chance level, and that as the differences in diameter increased, the proportion of correct answers also increased, exceeding the discrimination threshold and even approaching 80% of correct answers. And so the diameter difference for which the psychometric curve crosses the discrimination threshold we have set corresponds to the smallest difference in diameter that can be perceived by Pluck, which is 0.46 millimeters. Now, if we proceed identically for tension, it yields a JND of minus 46 newtons. So these JNDs, they gave us the minimum perceptible difference relative to a specific reference value. But the strings of Pluck string instruments vary greatly in diameter and tension, both from one instrument to another and within the same instrument. Therefore, in order to generalize these results so that they can be interpreted in a real-world context, we must calculate the Weber fractions of the diameter and tension through their respective JNDs and references. We find a Weber fraction of 1.53 for diameter, which means that one string must be at least 1.53 times thicker than the other for them to be discernible. And for tension, we find a Weber fraction of 0.4, which means that one string must be at least 0.4 times less tense than the others for them to be discernible. So these Weber ratios then allow us to examine the practical implications of the estimated JNDs by comparing them to commercially available guitar strings used by musicians. As I mentioned earlier, the tension and diameter of guitar strings systematically differ between two strings in the same set. So by comparing the difference in diameter and tension between the highest pitched string and the lowest pitched string of 6 different sets of strings, we are able to determine whether or not these differences exceed the Weber ratios we just found. So this graph shows the average differences in diameter and tension within the different sets of guitar strings I chose. And so the idea is to examine where these average differences are in relation to the Weber ratios we just calculated. And it turns out that on average, within each set, the difference between the diameters and tension of the lowest and highest strings never exceed their respective JNDs. So this information allows us to assume that the tension and diameter of the strings in the same set do not vary enough for the musician to perceive a difference by touch. That said, it's important to note that we are more inclined to make this assumption for diameter than for tension, given that the JND for the latter is fairly close to the average tension difference, which is clearly not the case for the diameter. So now, regarding the impact of string winding and their constituent material, given the categorical nature of the variables in question, it was necessary to find an alternative to JND as a descriptor of human tactile sensitivity. The experimental protocol for this study was similar to that of the previous study, involving a 3AFC task in which 3 strings were placed in front of the participant, 2 identical and 1 different, but this time the aim was to find the string whose material or winding differed. And once the different string had been identified, participants had to choose from a list of adjectives, the one that best described the perceptual dimension on which they relied for discrimination during the current trial. For the material, I chose to compare a fluorocarbon string with a steel string, two materials with notable differences in terms of surface condition, plastic properties, and thermal conductivity. And for the winding, I chose to compare a semi-flat winded string with a round winded string, which, as can be seen here, have marked differences in their surface topography and, by extension, in their linear density, but are otherwise identical. In addition to the variations related to the specific characteristics of the string, the person plucking them also has their own specific characteristics, which may influence the feel of the interaction to a greater or lesser extent. So inter-individual biomechanical differences are unavoidable. But beyond this aspect, the initial conditions imposed on the string at the moment of the gesture vary from one person to another, which, as Delphine Chatefaux puts it, contributes to the uniqueness of their sound signature. We can therefore assume that the level of expertise on pluck string instruments also influences the dynamics of plucking and consequently the perception of the strings. This led me to introduce the concept of expertise into this study, dividing participants into two groups. On the one hand, those who regularly and consistently play pluck string instruments using their fingertips, and on the other, those with no experience whatsoever in this area. This work also broadened the spectrum of interaction studied to include 3 interaction methods corresponding to gestures commonly used in guitar playing, and this using 3 distinct blocks. The plucking block, during which the participant had to pluck the strings, the pressing block, during which the participant had to press the string down to the fretboard, and the sliding block, which consisted in sliding the finger a few centimeters along the strings without pressing them. So during the discrimination task, the participant was either able to detect which string was actually different from the other two, which constituted a correct answer, or not, which constituted a fail. And so this graph shows the proportion of correct answers for all participants for each condition. The experiment was divided into 3 distinct blocks, during which participants had to find the different string either by plucking it, sliding it, or pressing on it. This task was carried out by 2 groups, the experts in blue and the non-experts in yellow, which ultimately gives us 12 proportions of correct answers, 1 for each condition and each group. So this graph provides us with a certain amount of information. First, we can note that there are only 3 conditions in which both groups succeeded in the discrimination task at a significantly higher rate than chance level. These 3 conditions are sliding on strings of different windings, as well as sliding and plucking strings made of different materials. In other words, this means that discriminating between strings made of different materials or windings by sliding is a relatively easy task, as is plucking strings made of different materials. Now, with regard to sliding, these results are not very surprising, given the particular sensitivity of the human touch when it comes to distinguishing between different surface conditions. When it comes to plucking, however, explaining this high ability to distinguish between 2 different strings based solely on their material is a more difficult task, as it is quite difficult to compare with the haptic literature. Plucking gesture being quite frankly very specific from a dynamic point of view, this interaction cannot be simply reduced to pressing the finger of the string until it's released. What we also see is that experts seem to exhibit a significantly better performance for both of these conditions. So this difference could be attributed to prior practical experience on pluck string instruments, but it could also be due to differences in the way the movement is performed by experts and non-experts, a way that improves the performer's instantaneous haptic perception. So to test this hypothesis, we'll have to look at the dynamics of the elements involved in this interaction, namely the finger and the string. Such, during the plucking block, a high-speed camera was placed at the end of the strings and pointed towards the plucking area. And after placing markers on the string and on the participant's finger, the interaction was filmed in order to capture all the subtleties of each movement for each participant. So through the measurements taken, I identified a metric related to the respective movement of the finger and the string that differs significantly between experts and non-experts, the complexity of the movement. Indeed, just by looking at the trajectories of the string, here shown as yellow and blue dotted lines, we can see that for non-experts, the beginning of the movement tends to follow a fairly simple trajectory, a straight line or parabola, while for experts, the overall trajectory is accompanied by sinuosity of varying amplitudes. This is what I call complexity. But this complexity has to be quantified in order to determine whether or not it differs significantly between the 2 groups. To do that, pluck complexity was defined as the lockstep Euclidean distance, or LSED, between the pluck trajectory and its smoothed version, which has similar overall trajectory to the original, but without the local sinuosity at onset of the movement. In order to make the complexity measurement comparable in between tests, we have to normalize the LSED by the total length of the curve. And so the normalized LSED is our indicator of the complexity of the plug trajectory. So after calculating the complexity values for each plug, I could produce this graph, which shows the overall distribution of complexity within the two groups, with the median complexity value represented by a dotted horizontal line and the interquartile range represented by solid lines. This graph clearly shows that there is a significant difference in complexity between the two groups. It appears that the plugs made by the experts describe a more complex trajectory than those made by the non-experts. That said, one might wonder whether a more complex movement is not simply the byproduct of expertise, and whether the difference in performance is simply due to prior row experience acquired by the member of the expert group. To clarify this question, we can take a look at whether within the expert group, greater complexity leads to a higher chance of success on the discrimination task. So here you're looking at the distribution of complexity among the experts for the trials that were successful in the discrimination task and its distribution for the fails. And so on this graph, we can see that there is a significant increase in the plug complexity for plugs that led to success compared to those that led to fails. Now, since we have a substantial amount of data, we can refine this analysis and divide the data into 4 quartiles and calculate the associated success rate for the plugs belonging to each complexity quartile. And the statistical tests run on all 4 quartiles as well as on the first and last quartile suggest, respectively, an association between greater complexity and a better ability to discriminate by plugging, as well as a significant difference between the proportion of correct answers in the first and last quartiles. So this sensory motor advantage, which seems to stem at least partly from the complexity of the movement, not only can we observe it, but we can also put forward some hypotheses as to why a more complex movement would improve discriminability in this context. First, we know that humans, consciously or unconsciously, employ specific exploratory procedures to optimize the extraction of targeted haptic signals. A straightforward example, we tend to use a static contact to evaluate thermal attributes, static contact that will prove uninformative when it comes to obtaining information about surface texture. In the specific case of our study, it appears that experts adopted an exploratory procedure characterized by a more sinuous trajectory than non-experts, which seems to have improved their performance in the discrimination task. So since the plugging duration and amplitude was not significantly different between the two groups, we can assume that the sinuous nature of the expert's movement induced a greater number of changes in direction within the same time interval, resulting in more dynamic haptic information. And so as this complexity induces variations in the force applied by the string on the finger in its direction or in the resulting biomechanical deformations, this greater number of fluctuations in the dynamic of the movement seems to have enabled the expert to extract a greater amount of dynamic haptic information about the properties of the string, ultimately leading to a better detection of the differences between the two. So far, we have shown that a variation in the characteristics of the string impact both the perceptive and dynamical aspects of the plug at microscopic scale. But during a plug, the string comes in contact with a quite reduced area of the fingertip, and add to it the very subtle differences specific to the strings, a macro-scale characterization of the interaction is not enough to measure the most subtle deformations of the fingertip, deformations potentially specific to each type of string. In order to study these local fingertip deformations, I developed a method that allowed for the characterization of the fingertip deformation during string plucking. So what I will present here is really just a proof of concept. The aim is to illustrate the potential of this method by characterizing a signal pluck. So the finger being a tridimensional object, we must obtain its displacement field in 3 dimensions in order to characterize all the deformations it is subjected to during the pluck of a string. And a method widely used to do that is the stereo DIC. So this method consists in filming simultaneously the object to analyze from two distinct point of views in order to reconstruct its geometry in 3 dimensions. So what I did is use a single high-speed camera oriented towards two 15 degrees inclined mirrors, which allowed to capture in a single frame a view of the fingertip from one side and the other. The idea is to reconstruct the geometry of the fingertip at each moment of the interaction and then to observe its evolution with respect to its initial state. So when the string was not yet in contact with the fingertip, leaving it undeformed. To reconstruct the geometry of the fingertip, we must be able to associate the left view of the fingertip with the right view, and this at each moment of the pluck. In order to do that, I applied black acrylic points all over the fingertip, creating distinguishable features that could be paired from one view to the other. But one problem that's very often encountered when using stereo DIC is to be able to track the respective displacements of each of the markers from one image to the other. Now, since the position of the string during the pluck inevitably induces a partial occlusion of the markers below it, and because the string slides on the fingertip during the release, the straight tracking of the markers is momentarily interrupted at some point of the interaction. So to solve this problem, I propose a custom method allowing for the estimation of the theoretical position of an occluded marker based on the variation of its Euclidean distance to its non-occluded k nearest neighbors between their previous and current position. This method, despite providing the exact position of the occluded marker, assures continuity in the tracking of each of the marker and allows for the estimation of the local deformations at every location on the fingertip, and this at each moment of the pluck. So first of all, the results I'm about to present are taken from a single pluck, so one video during which the participant plucked a 1 millimeter round winded string. So to analyze these results, I divided the pluck into 3 distinct phases. The compression phase, starting at onset of the contact and ending when maximal indentation of the string in the skin has been reached. The steady contact phase, starting when maximal indentation has been reached and lasting up to the beginning of string's release. And the sliding phase, going from the start of string's sliding up to the moment the string leaves the fingertip. Can I keep going or should I wrap it up? Yeah. So through this method, we are able to look at the displacement field's evolution along the axis normal to hands plane, and this for all 3 phases. So we have the surface of the fingertip undeformed, and little by little, we observe color variations representing the local displacement along a z-axis for each part of the fingertip with regard to its initial state. When we lean towards blue, it indicates an indentation of the skin, and when we lean towards red, it's an elevation. So during the compression phase, we can see a gradual indentation of the skin centered around the string, which is of course due to its actual indentation in the fingertip. You can also see that this indentation is not perfectly centered around the string, which is likely due to the fact that when plucking a string, you don't just press the string and then release it, but you will kind of drag the string towards you, so in the proximal direction, which would lead in a slight shift in the opposite direction. At the end of this phase, you can also see a beginning of elevation around the contour of the nail. So what I think is that this elevation comes from the anchor point function of the nail, which results in a concentration of the strains between the string and the nail, and then of an elevation. And this assumption is further reinforced by the fact that the skin located below the string does not present such elevations, which suggests that the absence of anchor point in that region allows for a more uniform distribution of the load generated by the indentation. And so the indentation of the skin reaches its maximal value at the beginning of the steady contact phase, during which it does not changes in amplitude or spread in a significant way, and the same goes on for the elevation around the nail. And finally, during the sliding phase, the indentation will progressively follow the displacement of the string and shift towards the tip of the finger while decreasing both in amplitude and spread until string release, during which the elevation will be more and more concentrated around the nail and eventually disappearing. So now if we look at the strain field along X, so along the principal displacement axis of the string on the fingertip, we also see lots of interesting stuff. So here the deformations indicate local elongations or compressions of the skin during the pluck. An elongation will lean towards red and compression towards blue. So during the compression phase, we observe a progressive elongation of the skin between the string and the nail, an elongation that doesn't reach its maximal amplitude and that does not extend all the way to the nail. And what we see is that this elongation will keep growing in amplitude during the whole standing contact phase, even though the string has already reached its maximal indentation at the beginning of the phase, as we've seen on the displacement fields. And so this late elongation of the skin, we can suggest that it comes from its viscoelastic nature. And indeed, it is likely that even though the string has already reached its maximal indentation, the skin does not comply instantaneously and keeps stretching all along the steady contact phase up to a certain threshold. And so this observation raises a quite interesting point. If we go back to what I've said at the beginning of the presentation, I have talked a lot about the dynamics of the string during the pluck and about the almost instantaneous temporal and spatial adjustments a musician exhibits along his movement in order to nuance it. The observation we just made highlights that the fingertip of the musician as the interface of the movement also shows a temporal dependency, and this at a very fine scale. This means that it constitutes a dynamical interface on its own, whose characterization is absolutely relevant in a fundamental analysis of a pluck. And to wrap this up, from that point during the sliding phase, we can see that the proximal part of the fingertip also undergoes an elongation that increases gradually in amplitude and spread. And what I think is that this elongation is mainly due to the friction forces imposed by the string on the fingertip when it is sliding on it, dragging the skin in the process. So all these observations, they will be precised in the foreseeable future through the characterization of multiple plucks. But for now, I think I'm going to wrap it up, and thank you all for your attention.
Thank you. If you have some questions, I think we can have some time later.
Yes.
Yeah, thank you. I would be happy to have some more details about the experiments during which you measure the threshold for tension on the diameter. So I guess that each had to realize several trials.
Yes. So in order for the results to be significant, you have to present each diameter or tension difference multiple times. I think it was 8 times.
And during between each trial, there was some kind of mechanical device which modified the order of the strings.
Well, you have the mechanical device just in front of you. I just kind of sweated a lot by changing the racks. So I had like, no, the mechanical device was not necessary at that moment, mainly because I still had to change the strings manually because like you could tense a string without removing it from the track, but for the diameter, obviously you have to change the rack on its own. So we did not do that far.
So you write some kind of predefined order.
No. For each participant, I knew how many times I had to present each stimulus, and then I had an algorithm that randomized the order of in order to not introduce any fatigue bias.
But the threshold you obtained were obtained for only one reference value.
Yeah.
Diameter. Beveridge law is valid. What do you have some other result with other reference values for diameter?
Well, this interaction is quite specific, so there has not been any work on determining the haptic sensitivity of human touch. But indeed, in the haptic community, we kind of suppose that the Weber's fraction is like works in most of the cases, but indeed we have this limitation that the extreme values, so for very thick or very thin strings, it would not be linear as presented here. So it's a tool that helps understand better, but it's not a said law and like. And I think if we had more reference string, like the same experiment with a different reference string, it could refine the Weber fraction I just found. But still, like even though it will be refined, it still won't be able to include the extreme values of diameter and tension.
I also would like some more information about the slide number 30. It's related to your preliminary experiment.
Yeah.
Not 30.
This one?
Yes, this one. I couldn't understand the results. Couldn't understand the task for the participants on the results. Sorry.
Okay, yeah, so I went kind of quick on this experiment since it's a preliminary study, but the idea was that the participants had to explore during 20 seconds the plate, and then they had to just to pick among all of these four categorical perceptual categories which one was most close at as what they had felt. And so the idea is that once the participant had explored all the types of like all the heating temperature with like during the parametric study, all the combination of parameters possible, then we were able to generally amongst all participants see in percentages what was most picked and what was not. So the idea is for the sticky zone, for example, participants, regardless of the parameters of the stimulus, 30% of the times they perceived a sticky zone. A sticky zone as a sticky area, or in whatever. Yeah. So we had a more precise analysis on well, different results that are more targeted. That I did not present here. It included also force measurements. So we had a force sensor under this, and we tried to find whether there was a correlation between the force applied and the stimulus perceived, and that was not. Yep.
Question about the
Stereo DIC. Mm-hmm.
So results on the grid.
So do you want to see the? Mm-hmm. Okay.
I was wondering, your grid is always the same from one image to the other. It's always the same grid.
You mean the array of markers, or?
Yeah. You use the mesh.
Mm-hmm.
Between the nodes of the mesh, you put the
No, so I did an interpolation of the mesh on the discrete values of my points.
Here you only show the displacement along the z-axis.
Along the z-axis, yes. Yeah, absolutely. It's just that I kind of had to choose which result was most interesting for you to see. But yeah, there were displacements also along the X or X. I also have. Yeah. Also for the deformations. But the thing is that what convinced me to show you these specific well, directions was that it's a single plug. So for the more subtle displacements or deformations, it was kind of difficult to interpret since we had only one plug, and so we couldn't make add different plugs and find specific features that always appear on during the plug.
Okay, thank you. If you have no other questions.
Maybe a last question coming back again to the diameter of tension part. I don't remember if participants could hear the sound produced by.
No, and they had also a damping pedal. So after they plucked the string, they had directly to press the damping pedal on the strings, so that if they put their elbows on the table, they could not feel the vibrotactile signals, and so no bias. Okay.
The last one.
Mm-hmm.
You consider two rooms full of experts.
Mm-hmm. Yeah.
Yes, that experts are guys.
Mm-hmm.
So they have different fingers
Mm-hmm.
than non-experts.
Yeah.
The skill is very.
Mm-hmm. Yeah.
And that affects the something like sliding.
Well, I think the fact that it's harder might impact the vibrations transmitted to the fingers. So maybe higher frequencies would be better transmitted to the sensory receptors. We have not put accelerometers on the fingers, so we don't know that for sure. But the idea is precisely to know what happens at the mesoscale on the fingertip, and this with the last experiment. So I will be able to determine, not for the vibrations, but if the deformation changes significantly between experts and non-experts.
The temperature, for instance.
Mm-hmm. Maybe, but actually the temperature, so I hadn't, I did not have the opportunity to show you the perceptual dimensions chosen by participants, but temperature was, I think, chose once amongst like maybe 300 trials I had. So it was kind of surprising and not surprising at the same time, now that I think about it. The temperature is like the interaction might be too fleeting, and the real area of contact not big enough for thermal properties to be perceived. So regardless of expertise, temperature was not perceived at all as a discrimination perceptual category. Okay. Thank you for your questions.
Thanks.